So, today I am starting the lecture 3 of module 4. I was continuing this loading condition, then we can convert the partial differential equation into ordinary differential equation, since the deflection and this load and other stress resultant will not be a function of theta. So, in that case we have seen that equation can be arranged and yield the desired deflection. So, after the deflection is obtained, then we can calculate the bending moment, shearing force and other bending moment and shearing force, because in that case the radial moment and tangential or circumferential moment, these two moments are of important in axial axisymmetric problem, but this m r theta that you because of symmetry and q theta is also 0. Okay. So, now let us show further application of this axisymmetrical formulation by giving more examples in practical cases. So, we will today discuss the bending of solid plate as well as annular plate supported in different manners and carrying the load in especially in case of this annular plate, or in some case you will find that specially for concentrated load that I have given in the first item, there you will find that discontinuity arises at the application of the point of concentrated load in the expression of slope and this when the concentrated load is acting just at the below the point of application of the concentrated load, the slope and deflection cannot be found out, but in the vicinity of the load this can be found out. In fact, there is no load which is concentrated, any load has some distributed area. So, practically if such load occurs in the plate, especially the concentrated load at the center, then we can find in the vicinity of the load the bending moment, and then we take the to the right and left of the load, and we can take the average of these two quantity to find the bending moment at the center. Okay. So, let us go to the topic. So, here a plate is shown of circular shape, thickness is h and the radius is a. It is subjected to a concentrated load P. Okay. Now, this plate may be supported in manner say that it may be clamped along the periphery, or it may be simply supported along the periphery, but since it is a axisymmetrical problem, this support condition must be also symmetrical about the rotational axis. Now, here rotation line of application of the load. Okay. Now, solve such type of problem by taking the differential equation of the equilibrium that we develop for axisymmetrical plate, but we can adopt to any of these two equations. One equation is that relating the fourth derivative of deflection to the distributed load, and the second one is relating the shear forces to the externally applied load. So, since there is no distributed load, the second option will be better in this case, because in absence of distributed load the forcing function of the differential equation cannot be written here. So, let us go to this equation, that the second equation which relates deflection with this third derivative of deflection with the shear force, that can be taken here with convenience. But another form is also existing, this relating the fourth derivative of the deflection to the distributed load, but this form cannot be used here because of concentrated load action. Okay. So, what we do actually, we take a slice of the plate at a radial distance r and consider the equilibrium of this slice. So, this slice is considered here, and equilibrium of vertical forces, especially to relate the shear force to the externally applied load, we will consider the equilibrium of the vertical forces. So, free body diagram showing the vertical forces are shown here in this figure, and now we can write the differential equation, the third derivative of the deflection to the shear force per unit length. So, the equilibrium equation now takes the form d by dr bracket 1 by r d by dr first bracket r w by dr bracket first bracket closed and third bracket closed equal to minus q r by d. So, this equation you can see this quantity is the slope d w by dr, and then it is taken to obtain the third derivative and to relate this to the shear load, shearing force. Now, observing the vertical force equilibrium of the slice in figure 2, figure 3 whatever you call, then we can write that any radial distance, the total vertical shear, that is q r multiplied by the length of the slice. Now, the slice is also a circular in shape. So, the perimeter will be 2 pi r. So, q r into 2 pi r is the total force. This must be balanced. We can write this with a positive sign and equate to 0. From this equation, equation 2, we get equal to minus p divided by 2. So, this is the equation for shearing forces per unit subjected to a concentrated load at the center at a radial distance r. So, now we can q r can be substituted in the equation 1, and then we can get the differential equation relating the concentrated load with the third derivative. Now, in order to do this, I write this substitute this q r with this minus p divided by 2 pi r. So, this equation now becomes this this d third bracket 1 by r d by d first bracket r d w by d r first bracket closed third bracket closed equal to p by 2 pi r d. So, this equation is actually the shearing force equation, and that has to be integrated to extract the deflected surface W. Now, the steps are underlined. So, integrating equation 3. So, if I integrate the equation 3, then I get the expression inside the third bracket directly. So, I get 1 by r d by dr first bracket r d w by dr, and in the right I will get because p by 2 pi d is a constant. So, p by 2 constant I can write here, but 1 by r integration will be log r. So, p log r is given in the numerator. So, p log r divided by 2 pi d, and then constant of integration appears and we name it as C1. Now, you can see that log r term is coming because of reciprocal of r that is appearing in the equation 3, and when we integrated dr by r, the log r terms appear, but mind that this log r has to be evaluated with respect to the base e. So, this is a natural logarithm that we have to evaluate. Now, let us proceed, go ahead. So, what we will do here, again you see we have to integrate, but before integration you are seeing that 1 by r term is associated in the left hand side. So, if I integrate this equation, then parts by integration by parts will give you a complicated expression, and you will not be able to get this W so easily. So, what can I do? I eliminate 1 by r, that means I multiply both sides by r. So, the right hand side you can see, then the right hand side there will be no differential coefficient involved. So, whatever the order of r or degree of r right hand side, it will not give trouble for integration. So, multiplying both sides by r, we now write d by dr r d w by dr and p r log r 2 pi d divided by 2 pi d plus C1 r, that is just after multiplying r with r we get this expression, equation number 5. Now, you can see I have marked it with red color r log r. because this appears of two functions of r. That means, when again I integrate, I require to integrate this expression r log r with respect to r using the integration by parts rule. Okay. So, now r log dr can be performed by the rule of integration by parts. Now, you have to note here very clearly that when I integrate this r log r, then log r has to be taken as the first function and r has to be taken as the second function. So, after integrating, we get in the right hand side that r log r integration is equal to r square by 2 log r minus r square by r. So, this is the integration of r log r dr. So, hence equation 5 after integration becomes this r dw by dr equal to p by 2 and this result I substituted here. So, r square by 2 log r minus r square by 4 plus C 1 r was there, C 1 r. So, integration will be C 1 r square by 2 plus C 2, another constant of integration. Okay. Now, here we are integrating a third order equation. So, naturally 3 constants of integration will appear. Now, we are reaching our target, that means, we have to obtain now the W, the deflected surface. So, the one more step is the, so divide equation 7 by r. So, we have done so that we get sole expression of dw by dr, that after this final integration we will be able to get w. So, both sides by r, we get in the left hand side dw by dr, that is the slope of the plate, equal to p by 2 pi d bracket r by 2 log r minus divided by r by 4 C 1 by r C 1 r by 2 plus C 2. Now, this expression represents the slope along any radial distance, because it is an axisymmetrical problem. So, at any angular direction it will be same. Now, you can see the features of this expression. At the point of application of the load, that is load is applied at the center, because it is a concentrated load. So, at r is equal to 0, you will get that dw dr is undefined quantity. So, that means, in the vicinity of center only the slope can be evaluated, but not exactly at the center. This is because of concentrated load acting at a single point. In fact, there is no such load acting at a single point. Load has some distributed area, okay, whatever small may be. So, finally, integrate equation 8. So, after final integration, again you see inside bracket r log r term appears. So, this expression can be used again here for integration. So, after integration, final integration, we get w r, that is w r is a w is a function of r, deflected surface is a function of r, because it is a axisymmetrical problem. So, there will be no variable theta in the deflection expression, because at any orientation the deflection value will be same along the radial direction. Okay. So, p by 2 pi d half r square by 2 log r minus 4 bracket closed minus r square by 8 second bracket closed plus C 1 by 4 r square plus C 2 log r, because C 2 by r term is there. So, after integration it becomes C 2 log r and the final constant is C 3. Okay. After this step, no more integration is required, because we obtained w r, that is the deflected surface. But still some tasks here you can see that there are terms which contains p, that is the load. There are terms which contains r square log r. There are terms which contains only r square, and there is also term which contains only log r and a constant. So, the constant arranged or clubbed together, and we can write that w r equal to a r square, that is r square term. We have isolated all r square term, that is here term is there, that this constant is named as a. So, a r square. Okay. then only the sole constant, that C 3 we have taken here and named as B, fresh we have named fresh as B. Then the term with P. So, the bending moment whatever we get is due to load P only. P does not exist in the expression fresh, then there is no value of this solution. Okay. So, here we get this term with P as P 8 pi d, you can see the product of this r square log r, and other terms we have just clubbed together with a constant B. Suppose P 2 pi d r square by 4, that constant is there, constant term is there with r square. So, it is plugged together with the constant A. So, final expression for deflection now can be written A r square plus B plus P by 8 pi d r square log r plus C 2 log r. So, constant of integration are A, B and C 2, that have to be evaluated applying the boundary condition at the edges. Now, you can examine the expression, nature of the expression, and you will be interested, because at the point of application of the load we will get the maximum deflection as well as we will get the maximum bending moment, it is obvious. But expression, if you put r is equal to 0, then deflection is not finite here, okay, because this term is becoming unbounded and this is r square. So, 0 multiplied by any high number will be 0. So, this term will give trouble in the expression. So, therefore, for final constant C 2, and therefore, final expression for the deflection can be written as W r equal to A r square plus B plus P by 8 pi d r square log r. So, this is the final expression for the deflection. Okay. Now, with this expression, that is concentrated load acting at the center, we can now proceed to evaluate the value of deflection, bending moment, etc., based on the boundary condition. Okay. Now, first let us consider a clamp boundary, that is plate is clamped at the periphery, a circular plate clamped or welded, a plate is welded at the periphery, or say for example, a circular slab in a assembly hall or somewhere in a temple, it is supported on a ring beam. So, is subjected to a concentrated load, there may be concentrated load or a load which is distributed over a very small area. So, in that case let us find out the maximum deflection, bending moment, etc. So, at r is equal to A, the edge is clamped. So, the limit of the plate is from 0 to A, the A is the radius of the plate, see this figure, and here therefore, we get the deflection at the boundary is 0 and slope at the boundary is 0 along the radius of the clamp condition. Now, applying the first condition in equation 10.1, what is 10.1? Let us see this 10.1. If I put r is equal to A, then to 0. So, A small a square plus B P by 8 pi d a square log A equal to 0. So, this we get here A square plus B plus P a square 8 pi d log A. So, this is the first equation finding the constant of integration A and B. Second equation has to be obtained by applying the condition on slope. At the clamped end, the slope along the radial direction is 0. So, the first derivative of is 0. So, we have to derivative of W. Since the expression for W is now known in terms of constant. So, we can obtain the first derivative of W. You can obtain this, the first term derivative with respect to r will be twice A r, derivative of B will be 0 because it is a constant, derivative of third term, that P by 8 pi d will be constant term, and here product of two terms are there. So, therefore, you have to differentiate r square first and coefficient will be remaining as log r, plus you differentiate log r and with that multiplication of r square will be there. So, using this we obtain the first derivative of this expression as 2 a r plus p by 8 pi d 2 r log r plus r. So, you can see here this expression is the result of the differentiation of r square log r. So, after differentiation of r square log r, it has decomposed into two terms. Okay. Now, since the slope is 0 at the Clem boundary, r is equal to a, now we apply the Clem boundary condition. Clem boundary condition is 2 a plus p by 8 pi d 2 a log a plus a equal to 0. This is the condition. So, now we get two equations. One is this equation relating a and b here, and here also another equation, but here b term does not appear because b is a constant which appearing as a sole term, and when we differentiate it, it vanishes. So, in this expression we get 2 a plus p by 8 pi d bracket 2 a log a plus a equal to 0. Okay. From this expression one can see that the constant capital A obtained as minus, I take this term in the right hand side. So, it becomes minus p by 16 pi d. You can see 2 is brought here. So, 8 into 2 16 pi d bracket 2 log a, because it is divided by a. So, 2 log a, and it is a by a is 1. So, we get the quantity or constant a as minus p 16 pi d bracket 2 log a plus 1. Equation 13, this equation 13. In equation 11, equation 11 is this, because equations the value of a, it gives the value of a in terms of known parameters, because p is known, the flexural digit which depends on the material constant E, then mu, and also the thickness of the plate is known, radius of the plate is known. So, the constant A is fully evaluated. So, after knowing the constant A, we can find the constant B from the expression 11. So, A is substituted from the previous equation here, and we can now evaluate B. After evaluating B, this B expression comes as B is equal to p a square pi d. So, we get the desired constants of integration that is required to fully know, completely know the deflected surface. Okay. Now, substituting A and B in the deflected surface that we have found from the solution of the differential equation, that is 10.1. 10.1, we will find that deflection equation now becomes W r equal to p r square 8 pi d log r minus p r square this becomes this W r equal to p log r minus p r square 16 pi d into 2 log a plus 1 plus the constant term. Okay. So, bending moment expression becomes the minus d second derivative of W divided by second derivative of W plus mu by r, mu is the Poisson ratio d W by d r. Now, after differentiating the W two times, and then we can get moment. So, bending moment expression is now written as minus p by 8 pi 2 plus log r square by s plus mu into log r square by s square. You can see the expression for radial moment. Examine the expression for radial moment. The radial moment at the center does not exist, because the slope is discontinuous, the first derivative is discontinuous, as shown the second derivative also. So, therefore, you have to find this the radial moment in the vicinity of the application of the load, but at the edges the clamped bending moment, that is fixed end bending moment, by putting A here, by putting A in the expression, A in the expression, we can get the maximum bending moment. So, when we put this r square by a square, r is substituted as a. So, this becomes 1. So, log 1 is 0. Similarly, this is also becoming 1. So, therefore, the maximum radial moment that is occurring at the clamped edge is equal to minus p by 4 pi. So, this is the value of maximum radial bending moment, and you can see that this quantity does not depend on the Poisson ratio. Now, let us come to the moment. Okay. The circumferential bending moment can be obtained by this expression minus d square w by dr square plus 1 by r dw by dr. Okay. Now, again substituting the second derivative and first derivative of the deflected surface, we get that m theta equal to minus p by 8 pi bracket 2 mu plus log r square by s square bracket closed v mu plus second bracket closed and the first bracket closed. Okay. Now, here you can see this expression m theta is not only dependent on the value of the load and the ratio of the r by a, but also it depends on the material property mu specially. So, at r is equal to a, again this term becomes 0 because log 1 is 0. So, we get the at the edges is m theta equal to minus mu into p 4 pi. Now, compared to the earlier value of the moment minus p by 4 pi, if you calculate this value, then you will find this moment is reduced because of this Poisson ratio effect. Okay. So, this is the then one can find also the shearing force, but shearing force can be found from the equilibrium of vertical equilibrium in the vertical direction or from the calculation finding the third derivative and equating to the shearing force. Okay. Because we know this deflected expression deflected surface. So, we can now obtain the derivative up to third order easily. Okay. Let us come to a case where the plate has a hole at the center. So, as I told you, this type of plate is encountered in practical application in several occasions. For example, a circular shaped water tank, elevated water tank is to be constructed, and then we arrange the column in this circumference of the circle. So, for this column which are arranged in the circumference of the circle, it will be convenient to adopt a annular rough foundation accommodating all the column. So, this type of problem is found application in practice, and plate theory for finding this stress resultant can be used. Okay. Now, here we are examining a case where the annular plate is subjected to a moment at the edges. So, at the outer edge the moment is m 2, at the inner edge moment is m 1, and you can see here that the inner edge has a radius of b, that means the radius of the hole is b and outer radius is a. So, total radius of the complete plate is a, but there is a hole at the center, concentric hole, the radius of the hole is b. Okay. So, let us solve this problem. Now, you can see that in the region B r by B r ranging from B to A, this region, okay, there is no distributed load. So, that means shearing force will be 0. So, based on that we can write this equation d by dr 1 by r d by dr bracket r dw by dr bracket closed equal to 0. So, this is the equation or expression for shear force and to 0, because no shearing action is taken place here, because no load is there. Okay. So, this the homogeneous solve to find the deflected surface. Okay. Now, integrate this equation. After integration, we get the quantity inside this third bracket, and the quantity is 1 by r d by dr bracket closed r dw by dr equal to C 1. So, CO because this is 0. So, after integration a constant term will appear. Now, multiply equation 25 by r. If I multiply equation 25 by r, then it becomes d by dr r dw by dr equal to C 1 by r. This expression can be again integrated. So, after integrating this expression, we get r dw by dr equal to half C 1 r square plus C 2. Then to obtain w, again the tricks have to be applied, that we now divide this both sides of the equation with r. So, dividing both sides of the equation by r, we get dw by dr equal to half r plus C 2 by r. Now, integrate equation 28. After integrating equation 28, we now finally arrive at the desired. So, w is now C 1 by 4 r square, because integration of r with respect to dr will be r square by 2. So, naturally 1 by 4 term factor is coming here, and this term will be C 2 log r plus C 3. Okay. Now, here we are getting 3 constants of integration as expected after final integration, and now the 3 constants of integration have to be found out applying the boundary condition at the edges. Okay. Let us consider the edges are supported, simply supported. Okay. So, that means at this outer edge a moment m 2 is applied and the inner edge m 1 is applied, and in the region 0 to b there is no material, that is a hollow section, hollow portion of the plate. So, for at r is equal to 0, there is no question of any stress resultant or deflection, because no material is there. So, this expression W r equal to C 1 by C by 4 r square plus C 2 log r plus C 3 is valid only for the region r in between B to A. So, only in this region it is valid. So, we can keep now all the terms. So, C 1 by 4 C 1 by C 3, all the terms now are important to find out the boundary conditions of the to find out the deflection of the plate. Okay. Now, at the boundaries we examine that the radial moment m 1 at r is equal to b. Okay. So, at the inner edge the moment that is applied is b, and it is a symmetrically applied moment, edge moment uniform along the periphery, inner periphery and outer periphery. So, that you have to, it is bending under the symmetrical moment, because if the moments are anti-symmetrical condition, the differential equation cannot be used. So, m 1 is existing at the inner edge. So, therefore, at r is equal to b, we now equate the bending moment m r to m 1. Okay. The expression for m r is minus d bracket the curvature, that is the second derivative of w with respect to r, and then plus mu by r, mu is the Poisson ratio and shaded. First derivative and second derivative both have to be found out. Now, here you can see after differentiation and applying the condition at r is equal to b and r is equal to a, that is the inner edge and outer edge, we get two equations. The first equation is after application of the condition of radial moment at the inner edge at r is equal to b, we get d bracket C 1 by 2 1 plus mu minus C 2 by b square 1 minus nu bracket closed equal to m 1. And then after applying the boundary condition at the outer edge, that is r is equal to a, we get d bracket C 1 by 2 1 plus mu minus C 2 by a square into 1 minus mu bracket closed equal to m 2. So, two equations now we get, and two equations can be solved for C 1 and C 2, and after solving C 1 and C 2 we go for finding the constant, another constant C 2, but application of two boundary condition gives only the two equations. You see there are three constants of integration, but we get only two equations. So, let us see how the third constant can be evaluated. First, let us obtain the two constants of integration C 1 and C 2. Solving C 1 and C 2 from equation 30 and 31, that can be solved because this is a linear equation with C 2, C 1 and C 2. So, it can be solved by Cramer's rule or by simply this any method you apply from algebra, you can get the value of C 1 and C 2. Okay. So, obtaining the value of C 1 and C 2, we can write now C 1 equal to 2 multiplied by a square m 2 minus b square m 1 divided by 1 plus mu d bracket a square minus b square. Then C 2 is equal to a square by b square m 2 into m 2 minus m 1 bracket closed divided by 1 minus mu into d by into a square by b square. So, these two constants are obtained where a is the outer radius and b is the inner moment and m 2 is the outer moment. So, that has been shown in the figure. So, other constant C 3 is found from the fact that in the simply supported condition at the edges, say at outer edge the plate is simply supported. So, at r is equal to a, deflection must be 0. So, based on that we get another equation. So, substituting r is equal to a here in this expression, we get C 1 by 4 a square plus C 2 log a plus C 3 equal to 0. Okay. So, this equation we get. Now, combining this term, that is C 3 is equal to minus C 1 by 4 r square plus C 2 log r by a. So, these two terms we have got now, two terms C 1 and C 2 already calculated. So, now substituting C 1 and C 2, you can now get C 3. So, C 3 is calculated as this, C 3 is equal to minus a square by 2 into a square m 2, m 2 is the bending moment at the outer edge, minus b square m 1 divided by 1 plus mu into d into a square minus b square. So, three constants of integration is now completely known, because we require only three constants C 1, C 2, C 3. Three constants are appearing because we have integrated a third order equation. Instead of fourth order equation, we have integrated a third order equation. So, three constants are appearing. Now, three constants here are completely known. So, we can write the expression for deflection and m 2 is equal to 0. For example, here there is no moment at the outer edge, only the inner edge moment is acting. So, put m 2 equal to 0 in the expression, this expression, and then we can get the expression for W r as this. Okay. Now, let us see how the deflected surface varies with r by a ratio. So, the range of r is from b to a, b is the inner radius and a is the outer radius. So, we have taken the inner radius as 1/4 of the for example, to illustrate the solution, we have taken the inner radius as the 1/4 of the outer radius, and we have taken it is a steel plate whose Poisson ratio is 0.3. The variation of W r with r by a is shown in this figure 6. Here you can see this is the end 0 is the center, this is the center and this is the outer radius. So, variation of deflection with r by a ratio for simply supported circular annular plate subjected to edge moment is shown only for this edge moment m 1. Now, you can see here that at the simply supported edge the deflection is 0, obviously as expected, and at the it is not going at the center because center there is no material. So, at 0.25, because r is equal to only 0.25 a, because we have taken r is equal to a by 4. So, you can see that at r by a by 4, that is at the inner edge, because this is free, the maximum deflection is occurring here. Okay. So, in such a manner we can find the expression for the annular plate. Now, here another variety of problem I am discussing. This problem will be slightly complicated, because the loading is not continuous, because there is a break in the load, although it is axisymmetrical, but there is the load is not containing the full plate. This is also a plate with hole, the radius of the hole is b, but the loading portion is from C to A, that is C is the radial distance from where the uniform load starts and it ends at the outer edge A. The hole with a radius b in the plate exists. Okay. Now, here we have to obtain the solution in two cases. That means, first we have to get the solution for inner region and then we have to get the solution for outer region. Inner region I am calling that region where there is no load acting, and the outer region I am calling this portion where the load is acting. Okay. So, inner part is say B to C where no load is acting, and outer part is from C to A. Now, if I see the vertical force equilibrium in the outer part, we can see that total shearing force at any slice will be 2 pi r q r equal to total vertical acting on the slice. So, total vertical load acting on the slice will be the area will be pi r square minus c square, and q is the load acting on the slice. So, this is the total external load that is acting on the slice should be equal to the total shearing force. So, from that condition we can get q r equal to q by 2 r bracket r square minus c square. Okay. Then we use the deflected we should find the deflected surface by integration procedure, and we adopt the equation third order equation where shear force is related to the third derivative of the deflection. Okay. Now, here if you solve this by substituting q r that we have obtained here, we can get a solution W. Now, this solution contains 3 constants for the outer region. Okay. Then the inner region also will get a solution. Inner region actually no this force is acting. So, naturally this, but we get 3 constants of integration. So, 3 plus 3 6 constants of integration have to be known by applying the boundary condition. So, boundary condition we require 6 in numbers to be applied for to know all the constants of integration, and then we can finally know the deflected surface. For the inner part, if you see that r is equal to b, no moment is acting because it is a free end and no externally applied edge moment is there. So, therefore, we take m r is equal to 0 at r is equal to b. So, this is one condition. Then for outer region or outer solution, if you call that we have obtained where the load is considered q. Second condition is at simply supported n, that is the radial moment is 0, m r is 0, that is second condition. Then deflection is 0 at the simply supported n, that is another condition. So, we get 3 condition to be imposed on the 2 differential equations involving 6 constants of integration. Then another 3 constants are found at r is equal to c, that is this point. Deflection found from the inner part should match with the deflection found from the outer part for satisfying the compatibility of deflection. So, compatibility of deflection has to be satisfied at the common point. So, at r is equal to c, W inner equal to W outer. Then fifth condition is the slope compatibility has to be satisfied at the common point. So, at r is equal to c, again dw by dr inner equal to dw by dr outer. That means, outer and inner solution differentiation has to be taken, and has to be equated. Last boundary condition is the bending moment mr, that is the radial bending moment at this common point on the inner part should be equal to the radial bending moment at this point from the outer solution. So, in this way we get the 6 solutions, 6 boundary conditions, and applying 6 boundary condition, 6 constants of integration can be evaluated. Okay. Now, lastly I want to discuss a problem of finding the deflection and bending moment in a circular plate carrying concentrated load at the center, whose boundary condition is simply supported. So, that type of problem is also occurring in practice, that is the simply supported edges, and let us see how to solve such problem. Okay. So, we have here this problem of simply supported plate. Circular plate, that means we have a plate which is simply supported at the edges. And carrying a concentrated load. Carrying a concentrated load at the center. That means, if you see a section and at the center there is a load. Okay. So, let us solve the problem of finding the deflection. Okay. The equation of the plate deflection is known. We can take the third order equation, we can take the fourth order equation. Okay. Now, here we shall take a slice around the load and consider the equilibrium of the slice. Okay. So, load is acting here P, and we have the shearing force that is acting around the slice of magnitude q r per unit length. Now, from vertical force equilibrium, that is summation of forces in z direction is 0, z direction is the vertical, this is the z direction, and direction of w is also. Okay. So, taking the equilibrium of forces, summation of forces in the z direction to be 0, we now get 2 pi r q r, because we take this slice at a distance of r, okay, equal to this p, or we can, because it is both are taken this downward. So, it will be minus. So, q r is now equal to p by 2 pi r with a minus sign. Okay. So, this is the q r. Now, let us write the equations of equilibrium, differential equations. So, differential equation okay. Let us write like this: d by dr 1 by r d by dr r dw by dr minus q r by d. Instead of q r, now I put this term. So, this term is brought here, and now differential equation can be written is p by 2 pi r d. Okay. So, instead of p q r, we have now written minus p by 2 pi r. So, this equation now becomes d by dr 1 by r d by dr r dw by dr equal to p by 2 pi r d. Okay. Now, integrate this equation. Integrating the equation, what we get actually? We get this W r, because integration have to be carried out, the result is known to us, a r square plus b plus p by 8 pi d r square log r plus C 2 log r. Now, for deflection to remain finite, for W r to be finite at r is equal to 0, that is at the center, we drop C 2. So, therefore, final expression for deflection becomes a r square plus b plus p by 8 pi d r square log r. So, this is the final expression for deflection. Now, if you see this deflected surface, then you can find the two constants of integration a and b by applying the boundary condition. So, if I look towards the boundary condition in the previous slide, boundary conditions are, that is a circular plate was there and this edges are simply supported. Edges are simply supported. So, in that case, টাইম না লাগিব, আকৌ নতুন কৰি ষ্টাৰ্ট কৰোঁ, এইটো কাটি দিলে হ'ব। গম পাইছে না, এইটো কিয় আজি এনেকুৱা হৈছে? এইটোৱে আছে, না না এইটো আগতে গ'ল দেখি, এইটো কাটি দিম, এইটো মুছি দিম। নাই এইকেইটাতো অহা নাই, ওপৰতটো কিয় যোৱা নাই? আপুনি ওপৰত সিলেক্ট কৰা নাই, সেইকাৰণে যোৱা নাই। ওপৰত, এই ওপৰত যাওক। এতিয়া সিলেক্ট আৰু ওপৰতে। এইটো দুটা আছে তো, দুটা আছে, এইটো মাউচেৰে পাৰিব স্যাৰ, মাউচেৰে বেছি হেল্পফুল হ'ব। মাউচ, আচ্ছা, আপুনি এইফালে যাবলৈ মাউচটো ইউজ কৰিব। ইয়াতে লাগে না, আপুনি ইয়াতে লিখিব। ইয়াৰ পৰাই দিব নেকি? ইয়াৰ পৰাই দিওঁ, ইয়াৰ পৰাই দিওঁ। So, the equilibrium of vertical forces is considered for this slide, and we have seen that the q r can be related with the externally applied load as minus p by 2 pi r. So, differential equation of equilibrium is now d by dr 1 by r d by dr r dw by dr equal to p by 2 pi r d. Okay. So, obtaining this, we now go to finding the constants of integration. That means, the equation can be rearranged in this form, final form, and then we apply the boundary condition. So, boundary conditions are at say a radius a, r is equal to a, at the boundary, the deflection is 0 because it is simply supported, as well as m r equal to 0. There is the radial moment equal to 0. So, first condition gives this a square plus b plus p by 8 pi d a square log a equal to 0. So, this is one equation after applying the boundary condition. Second equation is obtained applying the radial moment condition to be 0 at the edges. Okay. Now, if I go in the finding the radial moment, then we should know the second derivative, first derivative and second derivative. Okay. Because the radial moment contains the curvature as well as the slope also in axisymmetrical system. So, dw by dr is now equal to twice a r plus p by 8 pi d 2 r log r plus r. Okay. And second derivative of this del square d square w by dr square equal to twice a plus p by 8 pi d. You see, this is the product of two functions. So, we are differentiating, and after differentiating we are getting say here 2 into say we are getting first say log r, then we are getting 1 plus 1 another term is there. So, final expression is second derivative is twice a plus p by equal to into 3 plus 2 log r. Now, apply the condition of bending moment. So, m r at r is equal to a to be 0. What is m r? M r is equal to minus d square w dr square plus mu by r dw by dr should be equal to 0 at r is equal to a. So, after substituting this value, this d square w by dr square and dw by dr with r substituted as a, we now finally get an expression of a. So, from that condition we get directly the expression for a as minus p by 8 into 2 pi d, because 2 is there.